Hi everyone, my name is Lazar Reich, and I'm here today to present a project I worked on with my friend Suhas Vijaykumar. The purpose of our project was to show that it's possible to reconcile two influential notions of algorithmic fairness that were previously shown to be in conflict with each other. Before diving in, I'd like to motivate this work with the real-world finding that helped kick off this area of research. In 2016, the news agency ProPublica issued a report arguing that a major algorithm in the criminal justice system is biased. They found that the COMPAS algorithm was about twice more likely to misclassify a Black defendant as high risk compared to a white defendant, and about twice more likely to misclassify a white defendant as low risk compared to a Black defendant. Now, when judges bail decisions and are informed by an algorithm like this, that raises the question of how actual defendants are impacted in practice. Of course, as many of us are aware today, the COMPAS issue was not entirely straightforward. In fact, the company that created COMPAS issued a statement saying that, in fact, they designed their algorithm to be unbiased. In particular, it satisfies predictive parity, or calibration, meaning that scores reflect the same average risk for members of both racial groups. And this figure from a Washington Post article demonstrates that indeed the COMPAS score seems to satisfy this condition. So two important criteria have come to the surface here. The first is equal error rates across groups, also called equalized odds, formalized in Hart et al. This says that the probability of being correctly classified as positive or correctly classified as negative does not depend on your group affiliation. There's also the condition of calibration within groups. This says that scores reflect the same true risk on average for members of both groups. And this is what COMPAS did satisfy. Since both of these conditions feel in a way fundamental, but an important algorithm satisfied only one, that naturally raised the question, is it even possible to achieve both? Influential results have suggested that the criteria are indeed at odds with each other. In particular, it's been shown that when groups have different mean outcomes, the following are incompatible: calibration of scores, and something called balance in the positive and negative class. This balance condition means that the average score of true positives should be equal across groups, as well as the average score of true negatives across groups. Meanwhile, a separate result proved that calibration of binary coarsened scores is incompatible with equal error rates. And together, these results were interpreted largely as evidence that the criteria are in fundamental conflict. For example, one paper wrote, "We show that the differences in false positive and false negative rates cited as evidence of racial bias in the ProPublica article are a direct consequence of applying an instrument that is free from predictive bias to a population in which recidivism prevalence differs across groups." And these results actually made their way into the press. The Washington Post had a headline, "A computer program used for bail and sentencing decisions was labeled biased against Blacks." It's actually not that clear. And ProPublica issued a follow-up article where they called the bias mathematically inevitable, according to researchers. I think that one of the reasons why these impossibility results were so interesting is that they expose an unintuitive but yet very important source of unfairness in algorithms. In particular, it was intuitive that when there's bias in our data and an algorithm learns on that data, it can replicate that bias. But here, we now know that even if there's no bias in the data, but groups simply have different average outcomes, it's mathematically impossible to achieve all notions of fairness we might want. Therefore, it's important to precisely understand the trade-offs and be clear about our priorities in each setting. With regards to calibration and equal error rates in particular, if we go back to the previous slide, you may notice that this first set of results applies notions of calibration and equal error rates specifically to scores. Meanwhile, the second result by Choldachova considered binary scores, which are essentially classifiers. Therefore, in that case, both criteria are taken to a classifier. And neither of these is the exact setup in COMPAS, where calibrated many-valued scores inform binary high or low-risk classifications. And this is what motivated us to take a second look at these impossibility results. Another motivation was that the COMPAS setup, where scores inform binary decisions, is one that we see again and again in practice, often with some sort of human decision maker in the middle. For example, child welfare agencies screen calls to investigate child abuse allegations. And doctors in some hospitals use algorithms to determine which patients may require an additional intervention. In cases like these, it may seem natural to wish for the classifications to ultimately satisfy equal error rates, and meanwhile to provide the decision maker with a score that's calibrated, that is, correct on average for multiple demographic groups. Now, we wanted to investigate whether both of these were possible. Can we give calibrated scores that at a group blind cutoff yield equal error rate classifications? Our contribution is to prove that yes, this is possible. Along the way, we fully characterize this set of feasible solutions, and we propose an algorithm that produces the most informative score that both satisfies the fairness criteria and then minimizes the decision maker's loss. We also provided some generalizations, including partial enforcement of the fairness criteria. And then finally, we applied our procedure to two settings. The first was criminal justice, where we show that it can correct the COMPAS error rate imbalances. And second, we compared it to the omission of sensitive features in a credit lending example. So let's talk some theory. The purpose of this section in particular is to prove that calibrated scores can yield equal error rate classifications and to show exactly when that's possible. A little bit of notation. We suppose we have some scores, p hat, that are probabilities ranging from 0 to 1, and they predict a binary outcome y based on features x. We think that the decision maker uses scores to produce binary classifications y hat. Individuals represented in their data come from two groups indexed by A, where the group L has a lower mean. The fairness constraints are specified here. We want scores that are calibrated within groups. This means that the probability that you're a true positive, conditional on your group and your score, should be independent of your group, and in particular, should equal your score. We also want the ultimate classifications to satisfy equal error rates, meaning that the probability you're classified as positive, such as, say, the probability you're granted a loan, given the group you belong to and your true creditworthiness, is independent of the group you belong to. So as you may notice, one condition here is about scores, and the other is about classifications. So for tractability, we need to find a way to relate the two. And that's why we need to understand the goals of the decision maker in the middle, who converts scores to classifications. So we use backwards induction to do that. In particular, suppose a decision maker is given a score that satisfies calibration. We ask ourselves, what does she do with it? We're going to suppose the decision maker regards false positive classifications as k times costlier than false negatives. If that's the case, one can show that given calibrated scores, the decision rule will be a group blind cutoff rule. That is, everyone with a score p hat greater than some cutoff p bar will be accepted. And p bar is increasing in k. Now, we're not going to suppose that we control p bar, but we do assume that we know it, or at least have some approximation of it. And therefore, we can rewrite our resulting fairness criteria. In particular, we want to be able to produce a score p hat that both satisfies calibration and also yields equal error rate classifications at the decision maker's favored cutoffs. So to go forward and characterize when such scores are achievable, we go in two steps. The first one, we characterized what error rates are achievable by classifiers that satisfy equal error rates. Then we put that aside and considered what error rates are achievable by classifiers that can be produced by a cutoff p-bar applied to some calibrated scores. And then finally, our feasible region is given by the intersection of those error rates. So first, we wish to characterize the error rates achievable from an equal error rate classifier. First, recall that if you consider the R2 space of true and false positive rates, then the full set of achievable error rates for a particular group is given by the convex hull of the ROC curve of the best score given the data, P star, and the worst score, 1 minus P star. Meanwhile, as Hart et al. Have shown, the error rates achievable by an equal error rate classifier is given by the intersection of these regions for the groups of interest. So shaded here is an example setting of all pairs of error rates that are achievable by an equal error rate classifier. Next, we're going to consider which in these set are achievable by a cutoff p-bar applied to a calibrated score. We find that achievable set through the following proposition, which is proven in the paper. It says that a classifier can be associated with a cutoff p-bar applied to a calibrated p-hat if and only if its group-specific positive predictive values exceed p-bar and its group-specific negative predictive values exceed 1 minus p-bar. And putting this together with the previous result, we can see that the desired score p-hat satisfying both criteria exists if and only if the following kind of classifier exists: one that both satisfies equal error rates and whose PPVs and NPVs satisfy the conditions in this proposition. So what we decided to do is use Bayes' rule to rewrite the proposition's inequalities so that rather than in terms of PPVs and NPVs, they're in terms of true and false positive rates. That way we can map the inequalities onto the same space as the equal error rate region and consider the intersection. So as it turns out, the PPV and NPV inequalities create two half spaces in the true positive and false positive rate plane, where any pair of error rates above both half spaces is achievable. So the overall feasible region is shaded in gray here. One thing that I think is interesting to note is that the position of those half spaces indicated by the dashed red lines are fixed by the group means and the cutoff p-bar, which we don't have control over. They're fixed by the setting we're in. Therefore, what determines feasibility is essentially the height of the ROC curves. Higher curves expand the feasible region. Well, how might we be able to expand the feasible region in practice? By acquiring additional data or enhancing the quality of our data in order to achieve a higher true positive rate for every false positive rate. And in that way, I think it's worth noting that data richness complements our fairness conditions here and increases the size of the feasible region. I'm sure you've noticed now that what we've done is characterize which error rates are achievable according to the fairness criteria. However, not how to actually compute a calibrated score that yields any of those error rates. So ideally, we wish not only to satisfy the criteria, but also to produce for the decision maker a very informative score, one that they can trust, that conveys the strength of the algorithmic prediction. If that weren't important in practice, then algorithms today would output just binary recommendations rather than many valued scores. So our next order of business was clearly to propose an algorithm. Our priorities were as follows. First, we wanted to achieve the fairness criteria. Then, subject to those criteria, we wanted to minimize the decision maker's loss, which in a way is like maximizing accuracy. Finally, we wanted to produce a score that is as informative as possible. And overall, our algorithm achieves these priorities by proceeding in two stages. In the first, we identify what error rates minimize the decision maker's loss within the feasible region. And then in the second step, we post-process the Bayes optimal P star into the most informative score that achieves those target rates from stage one. So I'll just briefly speak to the intuition of each of these stages. In the first stage, we start by computing the feasible region. That involves first estimating P star, the most accurate possible score irrespective of fairness conditions, tracing out the ROC curves, computing the half-space constraints, and getting the fairness feasible region, which here is illustrated in gray. Now you may notice this feasible region is convex, and each point within it is associated with a linear loss to the decision maker that's in particular based on the relative preference for false positives or false negative classifications. And thus, this stage is a simple convex optimization problem. We'll end up somewhere on the top left frontier of this gray region with a particular point based on K, the relative preference for false positives. So in our draft, we actually generalize this stage in a few different ways, such as what if you only want equal true positive rates? Or what if you only knew the cutoff with some error? But for now, we'll just stick with the basic form. So stage 2 of the algorithm. Now that we've decided what are our target rates, we asked ourselves how to deliver a calibrated score that achieves those rates at the cutoff p-bar. We noticed that the best fair score is recoverable through post-processing P star. That can be proven. And this is what motivated us to define a constrained optimal transport problem. That is, to take the masses in the distribution of P star and map them to the distribution of some fair P hat. Now, what do I mean by constrained? Well, we want P hat to satisfy certain properties. It should be a valid probability distribution, the resulting P hat should be calibrated, and it should achieve the target error rates chosen in the first stage of the algorithm. Now, what do I mean by optimal? Well, we want the p hat to minimize mean squared error subject to our constraints. In the paper, we show that you can actually control the excess error by simply controlling the difference, minimizing the difference between the new p hat and the original p star. And that's true even if the p star is an approximation of the Bayes score. So allow me to show you a couple examples of this procedure taken to data. We found that there are broadly two kinds of applications our work can be relevant to. The first is an algorithm that outputs both a score as well as a binary recommendation. Our algorithm can help produce scores that are calibrated and binary recommendations that yield equal error rates across groups. So one example of this is the COMPASS algorithm. What we did is we used existing COMPASS scores to trace out ROC curves, and we applied our post-processing procedure to create new scores. As you can see in this figure, with the little white cross, our procedure is able to bridge the error divides across groups. In the paper, we also present evidence that the procedure continues to maintain the calibration of COMPASS. Then we were interested in another example, specifically to test out this idea of a decision maker in the center who uses scores to make impactful binary decisions. And so we turned to credit lending. We suppose the lender asked us to construct fair scores to aid their classification task of approving or denying loans. And for the purpose of the illustration, we assumed the lender finds false positives 10 times costlier than false negatives. That is, that defaulters are very costly. So we used the Survey of Income and Program Participation, which is a nationally representative survey with thousands of features. And we regarded the outcome as the reported ability to pay rent, mortgage, and utilities in 2016. And we predicted that outcome using survey responses from 2 years prior. We distinguished groups by education. In particular, less educated individuals had a default rate of about 11%, while higher educated individuals had a default rate of about 7%. We had a few different comparisons. One was to a strategy based on the omission of sensitive features, that is, predicting as accurately as you can, exclusively with financial data. Yet our procedure itself is based on all the data we have access to, not just financial data, but access to social programs, demographic features, and things that are ordinarily viewed as sensitive. we were interested in seeing how the two compare. So one summary of this is given here. The black diamonds indicate the error rates for high and low educated groups when you use all the data and no post-processing. Then we applied our post-processing procedure specifically to equate the true positive rate to ensure that qualified individuals in both groups have the same probability of accessing the loan. And as you can see in this figure, the two groups' true positive rates basically are bridged through this procedure and they meet in the middle. I think one more interesting comparison is given by the circles in white. This is based on the omission of sensitive features, which is the common practice used today. As you can see, when you use all the data and post-processing, both groups' true positive rates go up. That is, qualified individuals from both groups can benefit. And it probably also doesn't come as a surprise that the addition of data and informativeness also improves the lender's profits. So overall, our goal here was to present one path toward fair prediction in cases where a risk score informs classification task. We characterize the whole feasible region of where calibration and equal error rates can be reconciled in this way. And we propose an algorithm that produces a score that's both informative and that satisfies the fairness criteria. Along the way, we emphasize the importance of data richness and how it complements these notions of fairness. So thank you so much for your attention. We're looking forward to discussing and learning from you throughout the rest of the conference.